Hello everyone, welcome to the course Electromagnetic Theory. My name is Sheikh MD Buland Tasneem and I am a faculty and departmental head at the Department of Electrical and Electronic Engineering, University of Scholars. I will be taking this course in this semester. So all of you are stuck with me for 6 months with this particular course. So today we will first look at what electromagnetic is. Now before start studying a subject, one has to know what is the subject that one is studying. And then that essentially leads to second question, right? That why should one bother studying this course? In other words, where does electromagnetics fit in electrical engineering curriculum? We will also discuss the syllabus, topics, course plan, and the textbook that I am going to follow in this course, which will be given to you at the end of this lecture. And we will begin by first defining electromagnetics in its broadest terms. Electromagnetics is essentially the study of interaction of fields that are generated by time-varying charge distribution and currents. Now, this definition does not probably mean anything to you at this point because the question that you can immediately ask is, what is a field? We said that electromagnetics is the study of interaction of fields, right? That are generated by possibly time-varying charge distribution and currents. So the question that should naturally come up is, what is a field? Then how are these fields generated by charge distributions and currents? How do a particular charge configuration generate a given electric field or a magnetic field? And how would a current distribution generate a magnetic field or an electric field? So these are the questions which one should ask. And then, what is the interaction between these two fields, the electric and the magnetic fields? So this is a broadly scope of this course. We will be looking at all these questions in greater detail. The reason why we are looking at electromagnetics is that if you complete this course successfully, this is the foundational course for your advanced courses, such as microwaves, radars, antennas, integrated optics, and maybe, of course, fiber optics as well. So without further ado, let us just warm up electromagnetic theory. Most of us are coming from circuit theory background, right? And this course is usually offered or taken by electrical engineers, electronic and communication engineers, and also telecommunication engineer students in their second or maybe probably the third year of their curriculum. So you have all the exposed to circuit. So you have all been exposed to circuit, right? You have done a couple of courses in circuits, filters, networks. So you are familiar with these terms. And you might be wondering, what is this electromagnetics that one needs to study? Is not circuit enough to understand? whatever that is there in electrical engineering? So these are the questions which one should ask, right? So the goal of the next few minutes is to show you where electromagnetics is necessary to be invoked or to be used, and why circuit theory in certain situations fails to give correct answers. To do that, let us first look at this particular circuit here. We have a signal source. This signal source is probably also be a battery or any kind of source. Then there are long pair of wires connected with the source, which is showing in orange color in the presentation slide, right? These wires can be assumed to be ideal. So both the wires are exactly same, and it is ideal. The room temperature, the properties of the molecules of the wires, all are same. So they are ideal. So now at some time t equal to 0, we are going to connect the two wires to the signal source, right? So there is a switch. So if we connect, that's the starting time. We call it t equal to 0. Now one can possibly come with different answers. So the first answer that one would come up is maybe nothing will happen. Or then one can say, no, current will flow for some time and then nothing will happen. One can also say that the problem is not completely defined in the sense that I have not told you what is the length and the shape of the wire. I have also not told you what is the frequency of the source. Would all these things matter? Let us look at each of these responses individually, and we understand where the limitations of circuit theory lies. From our circuit background, we might first think that, well, circuit is not closed, which means that there cannot be a current flow in the circuit. However, the voltage that is there at the source end will directly be available at the load end, right? The open circuit voltage of the source will be equal to the voltage at the load end. Now, frequency of the source and the length of the wire does not really matter to us, the electrical engineers. Because, as we know, if we provide a source and we connect any type of wire and there is a load, so the voltage at the source end must be dissipated across the load end. So we should get the same voltage dissipated at the load end, right? Now, that is what circuit theory would tell us. So, in a sense, if you are a circuits person coming purely from the circuit background and not knowing anything about electromagnetic field theory, you might be seeing this physical situation in which I have a voltage source, I have a switch which is closing at t equal to 0, and a pair of wires are something like this, right? Which is shown in the diagram. The important point to note is that in circuit model of this physical scenario, the length of the wire and the frequency of the source do not matter. Now, from our earlier physics course, we know that a battery is essentially source of electrons and ions probably, right? And if we connect that to a pair of electrodes which are made up of metal, then there must be some amount of charging that happens, which is similar to capacitor theory, right? So there is a charging, and this charging current must flow for some time until the wires are charged. And so the question is, how exactly does this mean? I mean, what process causes the charging of the wire? Or what is the exact voltage waveform? Does that depend again on the frequency of the source? So these are the questions that cannot be answered from the circuit point of view, because circuit theory does not consider these issues. So we need to know something else beyond circuit theory to answer these questions to the charging process, the shape of the current waveform, and for how long that charging current would flow. So let's go to the shape of the wire. Let's talk about that. Now, let us also look at the shape of the wire. I mean, this is something that you can do in your lab or in your house, provided you substitute certain components over here. You take a signal source, or you can take a battery, it does not really matter. You take a switch, and then the two long pair of wires that we have considered. You take one of the wires and sort of bend it over, okay? Just as shown in the diagram or in the presentation slide. There is no necessary that it has to be bent in a square form, but you can just bend it anyway, but you make sure you bend it significantly, okay? And then you connect a resistor at the other end, which means the load end, and then hook up the output of the resistor to the oscilloscope to see the output result. So you can clearly see the oscilloscope that oscilloscope is connected to the resistor end, and what is that we would obtain at the oscilloscope from the particular physical scenario. Well, going back to circuit person, as we have already said, this length of the wire, just because it is bent, does not really mean anything. The voltage after switching at this point will exactly equal to the voltage across the resistor. So it should be like that, even if you bend the wire in the middle portion. The source and voltage should be dissipated across the resistor for the circuit persons. If it is a sinusoidal waveform, you would expect to be a sinusoidal waveform on the oscilloscope as well. However, as you start increasing the frequency of the source, it turns out that at significantly high frequencies, the wire will actually cause the voltage across the resistor to drop to zero. Now, this is something that one cannot understand from the circuit point of view, because of the circuit people, this bent wire is equivalent to a straight wire. There is no reason why the shape of the wire should influence the output voltage across the resistor, right? This is what circuit people think. Now let's see what electromagnetic person would visualize this as. Let's go to the next slide. So for an electromagnetic person who will study this course, what he or she would see is that the same bent wire plus this other unbent wire or a straight wire at low frequency looks like an inductor, and at high frequencies looks like a transmission line. Okay, so these are the two differences. If an electromagnetic guy sees this same circuit at low frequency, he or she will see it as an inductor, and if the frequency of the source is very high, then it acts as a transmission line. However, both inductance and transmission line are concepts that are not actually developed from circuit theory. In circuit theory, if you remember, we just are given that we have an inductor, we have a capacitor, we have a resistor, and we are told how we haven't told how exactly to calculate these things. So what is inductance and how do we calculate it requires us to go beyond the circuit theory or circuit point of view to really answer these questions. Now let us do this exercise in which we take the wire, we make it straight, but then we cut the wire into two halves. So basically replacing the mid portion of the wire by two plates. Two metal plates. Now we apply our certain voltage in our function generator. And what do we expect to see at the output of the resistor? Clearly, there is no continuity of the wire between the two plates over here because the plate is broken, right? However, we do know that this situation is exactly that of a capacitor, which again comes back to the same question. Just what is capacitance and how do we calculate it? We know that the current will be continuous, that is, the current that is going through here must be coming out at the same current. Voltage will be different. Voltage will be in different phase, right? But the current will be at the same phase. So the current that is flowing here at one plate must also be the current that is exiting the other plate. Now, what exactly goes on in between the two plates is something that electromagnetic theory will help us to understand. Finally, we come to the length of the wire, okay? In circuit theory, again, length of the wire or interconnect between two gates. The two gates are the source and the load, right? Or two circuit elements does not really matter. It could be any length, but what we assume is that the voltage at one end of the wire or the interconnect is exactly same at the other end of the wire. So that is, if you can take the length of the wire to be, say, 1 kilometer or even 2 kilometer or even more 3 kilometers does not really matter for the circuit people. Whatever voltage that is over here should be the voltage at the load end. What I mean is, whatever voltage you are supplying at the source end, the length of the wire basically does not matter anything. It could be 1 kilometer, 2 kilometer, 3 kilometer. But for the circuit people, if you apply some source voltage at this point, it will travel and get dissipated at the load side. So the same voltage should show at the load side, irrespective of the length of the wire. Okay? So if you apply a sinusoidal voltage, this is shown over here, right? So please note where the maximum is occurring. At some time t equal to 0 point, the maximum of the voltage source is going through the maximum. Here, this one. This is a sinusoidal wave. The maximum is over here at t equal to 0. So you will see how it behaves at the load end. However, what you observe on an oscilloscope at the load end that you put at the far end or the load end side, if you would think, is that the maximum does not really occur at t equal to 0. It occurs after certain time. And this time can be defined as the length of the wire divided by the source voltage you are applying. So this is the delay time. So this is actually confusing to the circuit people because the wire length should not matter. The resolution of this paradox is that a long wire actually causes delay, and voltage and currents are not really the scalar variables that we have thought so far. But there are other waves, and a wave that would have experienced a certain time delay of L by V. So this is the time delay. The delay is calculated by the length of the wire divided by the voltage applied when it propagates with the phase velocity of v volt. Now you might not really understand all this concept at this point, but just keep in mind that whenever a source and a load which are separated by a long distance, there is some delay involved, and this delay is not taken into account by circuits, whereas this is explicitly taken into account by electromagnetic theory. Therefore, if you actually take this scenario of having a source at one end and a load at say 3 or 4 kilometers away from to other end, then you would clearly see that there is a certain amount of delay in transferring the voltage from one point, that is at the source, to the load side. Now this is something that circuit theory does not tell us or you. That is the reason why we call circuit theory models as lumped parameter models or lumped circuit modeling. A lumped circuit is one in which one simply neglects this time delay. And therefore, there is no change in the voltage waveform that is at one end to that of the other end. And in other words, the length of the wire does not really matter. So now you know where electromagnetic theory is involved. Takeaway from the previous slide is that there is a certain time delay whenever you have a wire that is connecting two circuit elements. And this delay can be ignored in the circuit region because of the various reasons. We will talk about all these reasons in a later time. But this delay is not predicted by the circuits, whereas electromagnetic theory will incorporate this delay. So we have to consider the time delay, and if this delay is because the current on the wire is not really just independent of the distance, but it is actually a function of the length of the wire. That is, if you see the equation I function of z and t, so with z you have beta. Beta is the phase constant, and the phase constant is lambda is equal to 2 pi by beta. So lambda is the distance, wavelength of the wave. That is, if you take the direction of the wire in which you have connected as the z-axis, then the voltage at any point on the wire would actually be delayed version compared to the voltage at the beginning. So basically, if you change the length of the wire, if you travel from the starting point of the wire and with time, basically the current decreases as the length of the wire increases. So if the current decreases, your voltage basically drops at the load side. So this phenomena of time delay and thinking of current as a wave is not predicted by ordinary circuit theory, and it cannot even deal with such phase delay effects without explicitly involving this phase delay into circuit point of view. So what happens at very high frequencies is that the wires start acting like transmission line, where the phase difference or the phase shift between at the source end to the voltage at the load end becomes an appreciable fraction of 360 degrees. When it becomes an appreciable fraction of 360 degree, one has to explicitly take into account the delay that is there between source and load. So that leads us to the question as to what is a transmission line and how do we analyze this transmission line, as it is directly related to length. Now, you might ask, well, so far we have talked about circuits and electromagnetic theory, and we said that there are situations where circuit theory does not give you correct answers. whereas electromagnetic theory will give you correct answers or correct predictions. So what I mean, why should we bother about this electromagnetic phenomenon? Well, to consider a device which is very close to us, such as computer or a cell phone, each of these devices which essentially perform computing stuff, they actually contain millions and billions of logic gates. And these logic gates are all switching at very fast and very high speed. And the gates switching time, that is, if the gate goes from high to low, or from low to high, those switching times are getting shorter and shorter. Now you can have fast gates which switch in the order of 100 picoseconds. Now, if the interconnect is such that the delay of the interconnect itself is about 200 picoseconds, there are two gates. This is one gate, this is another gate. And the distance between them, we are calling it interconnects from this point to this point, or you can call it a transmission line as well. So there should be a delay. We are talking about that delay. Now, if the interconnect is such that the delay of the interconnect itself is about 200 picoseconds, then the voltage which this gate is switching from logic high to logic low, the same voltage will not be available at the same time. And then the second one will switch after a certain time delay. Now, when you have such interconnects connected, you know you have these different elements or logic gates connected together. If the difference between the two interconnects is large, then the voltage between the same source will not be the same at one logic gate compared to the voltage at the other logic gate. So it's a common sense. So at the source end, if you apply a voltage and there is a long transmission line between them, so that line is causing some delay. So you won't have the same voltage at the load end. So this is what they are actually interpreting. Then this might lead to inconsistent result and completely inaccurate result, right? The correct model of this scenario is to treat this as a logical element. Whatever that you are considering, and this is another logic element which is switching. However, the space between these two, which is connected by a piece of metal or a wire, and on the left side, these are known as interconnects, as transmission lines. Now, transmission lines are characterized by several characteristics. So we need to know those characteristics. So one of the most important characteristics of a transmission line is that of its characteristics impedance. How does the impedance behave? So here you can see that the characteristic impedance is given to be 124 ohm. The arrow shows it, right? And the time delay of the transmission line or the interconnect is given as 0.3 nanosecond. And if this is the source voltage, you can see that source is switching from logic low, which can be represented as 0 voltage, or logic high, which is 5 volt. So if you come to the this figure over here, this one, this is the source side. Okay, this is logical 0 and this is logical high, which is 5 volt. Logical 0 is 0 volt. So to switch from 0 to high, there is a time delay, which is 0.3 nanosecond. And then the signal becomes high for some times. And then again, at this point, the signal basically shifts from 1 to 0. So there should be another delay over here of 0.3 nanosecond. And this is switching from logic low to logic high in about 0.5 nanoseconds. Okay, the delay is of 0.5 nanosecond. And thereafter, it is constant for about up to 10 nanosecond and then switch back to logic 0, logic low again with an interval of 0.5 nanosecond, which I have explained on the board. This is at the source end. So we were talking about the source end. Now let's talk about the load end and how the wave shape will occur. Let's see that. There will be ringing effects. This square wave is just for the comparison. So you see the figure below your source, that is your load. So there is a square wave inside, okay? But basically the wave shape will be a ring shape, like it's a damping sinusoidal wave. So it should be like that. So there is a problem. So we cannot define these problems using circuit theory. So electromagnetic theory comes here. So you will see overshoot and you will see undershoot. Now this is something that one would not expect if you go simply by the circuit theory. So in order to obtain the correct output, in order to predict this one has to replace the interconnect by a pair of transmission lines, or actually a single transmission line. So we model this source by a voltage source with a resistance and the load by saying capacitive load, for example. And then this piece of wire, which is called as the interconnect, that connects the two logic elements as a transmission line. Now you might ask, how do we calculate this transmission line characteristic impedance? What is transmission line? How do we calculate this time delay, TD? And what do these impedance ZC and the time delay TD variables have any effect on the load voltage? So these are the questions one might ask. We know that there is a load which is not exactly equal to the source, but how is this voltage at the load related to the transmission line effects? Let's see. Again, we have to go back to electromagnetic theory to understand where these parameters are coming from. For example, if you want to calculate the characteristic impedance, if you remember the impedance definition, the impedance definition is voltage divided by current. It comes basically from the Ohm's law. However, we have seen that voltage and current are not just numbers. They are dependent on where you are measuring them, right? So these voltage and currents are more accurately defined in terms of electric fields and magnetic fields. So voltage is defined in terms of electric field and current is defined in terms of magnetic field. And when we excite a transmission line by a voltage and current, we say that electric and magnetic fields are generated. So this is electric field where the voltage lies, and when you pass a current through a conductor, a magnetic field, magnetic rings of fields are generated. When you apply voltage to these conductors, one becomes positively charged, the other becomes negatively charged, which creates an electric field between them. So from positive to negative, the direction of the electric field. So do not confuse, okay? And then to obtain the characteristic impedance, we have to relate the voltage V to the generated electric field. And we have to generate the current I to the generated magnetic field. And one cannot do so, that is, one cannot obtain or one cannot understand the electric and magnetic fields unless one studies electromagnetic theory. Electromagnetic theory tells us how voltage is related to electric field and how current is related to magnetic field. And these relationships in turn give us relation for a resistor. They also give a relation for an inductor and capacitor as well. This is how we exactly can model the physical phenomenon that we have so far discussed. Now, I think this is right time to just summarize what we have done for the first 20 minutes or more than 20 minutes, 30 minutes over here. Where is more than just a wire, right? What we see as a wire at low frequency and at the circuit level is not just a wire, because it can act as inductor, it can act as resistor, it can also act as capacitor, or in a worse scenario, it can act as a complicated or complex circuit that can be modeled as a combination of resistance, inductance, and capacitance. So these are the lessons learned. It can also act as transmission line. When the frequency of the source is very high and there is a relation between length of the wire and the frequency of the source, we will discuss that later. But again, the point is that a wire is not just a wire. It exhibits a lot of secondary effects, such as inductance, capacitance, and resistance, and all these combinations. And we need to understand electromagnetic theory to be able to account for these secondary effects. Now, secondary effects are very, very important when you are defining such high-speed digital systems or you are designing a RF circuit. Unless you understand these effects, your designs will not probably work in the correct way or as you have intended. The reason why this electromagnetic theory has to be studied is because the ordinary circuit theory cannot act for these effects, whereas electromagnetic theory can successfully analyze these effects. Okay. Then we have the fiber optic field. How electromagnetic theory is related to fiber optics. Well, though the time is short, I'm thinking of whether I should continue more today or maybe in the next class. Do we have time left? Okay, let's study a little bit, maybe 10 minutes more. It is not just circuits where electromagnetics comes up often. নামাজে যাবা? যাও, আমি একটু পরে নামাজে যাবো, তুমি পড়ে আসো। হ্যাঁ, আচ্ছা, তাড়াতাড়ি এসো। It is also that electromagnetics opens up a wide array of topics that one can specialize in. That is, one can find applications of electromagnetics in. Now, you must certainly have heard about fiber optics, or optical fibers are the ones which can carry 99% of the world's traffic, right? It carries a lot of data. So all the high-speed advantages that, all the high-speed data transmission that we are now familiar with is mainly due to the optical fibers and the ability of the optical fibers to carry this large amount of data with very little attenuation. Now, how exactly data, which is actually an abstract quantity or a voltage or a current, in the abstract quantity mapped into the voltage and currents, how would they be excited inside an optical fiber? How would they travel inside an optical fiber is something that electromagnetic theory will tell us. It tells us that light, which is approximately modulated by the source that we are, by the data that we want to transmit, actually goes through as modes inside a fiber. And these modes would travel. So there are these different modes which I have shown. These modes have certain numbers, certain subscripts. There are certain letters. So these are the patterns and modes. So this is one mode, single mode. This is multiple mode. So the signal is superimposed and sent. Here it is a single mode. Okay? And these are the patterns. It looks like that. You do not have to worry about these numbers or subscripts. They are just the different types of light distribution inside the optical fiber. To understand this, one needs to know electromagnetic theory. One views on fiber optic cable or an optical fiber as example of solution of Maxwell equation. And however, that comes out of the solution are called as modes. And these modes are essentially the electric and magnetic fields of the light that are distributed inside the fiber. So in order to know that, in order to know what is Maxwell equation, we have to study electromagnetics. So how electromagnetic theory is related with antennas or radars. Now you might go to antenna or radars. In radars, antennas are one of the major components. And in wireless communication, antennas are there everywhere, right? Without any antenna, one cannot have wireless communication possible. Now to understand how there, I have shown different types of antennas over here. These are all different types of antennas, waveguides. This is sample dipole antenna. This is a horn antenna. This is a reflective antenna, and this is microstripped antenna. So there are different types of antennas over here. The question is, how exactly does this antenna, the dipole antenna, differ from a horn antenna or a pyramidal horn antenna? How does that differ from microstrip antenna? What parameters makes the radiation pattern of this antenna be different? And how do we analyze them? How do we make use of these radiation effects and radiation patterns in something? Again, the electromagnetic theory will tell us, okay? So just to give you an overall perspective of electromagnetics, I am just going to list up here. You can see this letter. Well, I think I should continue this few topics in the next class because we don't have much time. So we have few more slides. This is 18. We have 23 slides for the first lecture. Maybe 2 or 3 will be missing as I'll be closing the session here. So thank you very much for listening to me. See you in the next class. Take care, everyone. Bye.